Hi, my name is Boris Alladassi. I'm a postdoc in the LIPCA lab at the University of Illinois. Today, my presentation is on how we are developing a new hierarchical model to improve genomic prediction across populations in plants. Okay, as a background, we have this figure showing the historical overview of key milestones achieved at the top in Mendelian genetics and at the bottom in quantitative genetics. In the middle, we have the purple zone showing how discoveries and methods from the two fields work together to create new tools. I want to focus on two tools here, QTL mapping and GWAS. They have been revolutionary in understanding the genetic basis of complex traits. However, they've also been limited to identifying only a few genomic variants with large effects that account for only a small proportion of heritability that leads to Manolio et al. To coin the term missing heritability. So genomic prediction came along to address this partly by modeling all the genomic variants across the genome, but most of the current genomic prediction model focus on the additive components of the genetic variants. And that has led to low prediction accuracy when we use one population to predict another population. We are now seeing some emerging models, such as the omnigenic model, that are trying now to incorporate the non-additive genetic variance components. So what is the omnigenic model? Essentially, it is categorizing the variant into two subsets. We have first the core genes, the stars shown on the left here, that are having direct effects on the phenotype. And in contrast, we have the peripheral genes shown here in the gray circle. They are interacting in a regulatory network to have an indirect effect on the phenotype. And in 2021, Matheson et al. Extended on some of the implications of the omnigenic model by showing that we would expect the core genes to have consistent effects across population 1 and population 2. And in contrast, the peripheral gene will have different effects because of the interaction in different networks between population 1 and population 2. So clearly there is a need to model non-additive genetic variants. Here, we are going to focus on a particular case of non-additive genetic variants, which is co-adaptive epistasis. It was proposed by Carl Borg et al. In 2004, whereby if we cross two lines, one with the genotype JJ, and the other one with the genotype LLLL, we can derive a bunch of progeny with the phenotype summarized on this graph. Some key takeaways from this graph. First, we can see that if we look at locus 1 on its own, there is no significant variance, right? Significant difference between the genotypes across locus 1. And the same thing applies to locus 2 as well. So if we're using an additive model, we will not be able to detect any of these two loci. However, if we have a look at the two-way interaction, then we start seeing some changes in the landscape. Now let's focus specifically on the locus 1, JJ, and then we can look across that. The highest phenotype is when we also have JG on locus 2. So in short, if we have also a look at genotype LL, the same thing is happening. So we see that the phenotype is being enhanced when the progenies have actually the parental genotypes, the original genotype. And so that's where the co-adaptive epistasis is coming in, where we have parental haplotype versus recombinant haplotype. So we are now modeling this by first fitting again the additive mode effect as usual. But then in addition to that, we are also incorporating explicitly the parental versus recombinant epistatic effects to quantify the effect of those haplotypes. And to go one step further, we are also regressing the additive effect of this loci on specific subpopulation. And that will help us to capture the specificity, right, of this population and improve the genomic prediction across subpopulation. So as an ongoing work, we are currently simulating different genetic architecture scenarios. And on the left here, we have purely additive case where epistasis is set as 0, and we can see the incremental due to additive effects. And then in the middle, we actually have no additive effect, but only epistatic effect. And we can see the change in the landscape of the phenotype as well. And finally, on the right side, we have both additive and epistatic effects. And we can see how it is enhancing the phenotype, especially at the parental genotype. So in short, this new model, we are very excited about it, and we look forward to uh, getting into a step where we can now make it available to the plant science community. On that, please allow me to say thank you to the Lipka Lab, especially uh, Dr. Alex Lipka, my PI, for his support and guidance, and also our collaborators at Colorado State University and the Roslin Institute, Illinois Compute. And I would like to say that this work is funded by NSF. Thank you for your attention, and I'll be happy to take any question.